Good morning, everyone, and welcome to exercise 3 on design space exploration. For the first task, we have to use the Pearson correlation coefficient to show that the objective function f depends parabolically on the design variable x. So we got some values given here for our design variable x and also for the objective function. So the y values are the objective function values for the objective function f. We got the formulas given here for mean, variance, covariance, and finally the Pearson correlation coefficient. Those formulas look slightly different to the ones that you've seen in a lecture, but if you want to take the time, it's not very hard to transform one into the other. If you use those formulas instead of the ones in the lecture, please take care of where those parentheses start and end, and also where the sums start and end. So that's important, and it's a pretty common mistake in the exam. The Pearson correlation coefficient is a coefficient that shows the linear dependence between a design variable x, I, and the output or the objective function y. So now if we want to show a parabolic dependence and use the Pearson correlation coefficient, which shows a linear dependence, we just have to substitute our design variable. So we introduce a new design variable x prime, which is the square of our old design variable or original design variable x. So our x prime, we just take the squares of 4, of 7, of 10, and of 13, and the y values stay the same. 20, 50, and 253.5. Okay, now if we show the linear dependence between our new variable x prime and the objective function y, we've shown a parabolic dependence between the old design variable x and the objective function. Okay, to compute the design variable, we start to compute the Pearson correlation coefficient, we start with the means. So the mean of x prime is just 1/4 because we got 4 samples over all the samples, values of the samples, and we plugged that into the calculator and got 83.5. We do the same for y. 150, 253, and we have 125.25. Secondly, we compute the variances. So the variance of x prime is 1/4, and then we take the square of the values and build a sum, and then we subtract 4 times the mean value, and this is 3,332.5. We do the same for y. I won't write it down here. I mean, you get the point. And it's 7,497.6. Finally, we need the covariance between x prime and y. And here we take the multiply the samples. So we'll build the sum over the multiplication. Plus 49 times 73.5 plus 100 plus 60.5. And again we subtract 4 times the product of the means. Oh, and I was missing a square here. 83.5 times 125.25, and then we have 4,998.4. Now we got all the ingredients, so finally we only have to plug that in. So the Pearson correlation coefficient is the covariance divided by a product of the variances. 998.4 over, and on the last slide we computed the squares here. So now we have to use the square roots. Of 7497.56, and if we plug that into the calculator, it's approximately 1.00. I wrote an approximately here because it's not exactly 1, although looking at significant figures, the samples were only given with 1 digit after the comma, and also we did some rounding while computing variances and covariance, so you could also write an equal here and that would be fine. Okay, now we've shown a linear dependence between x prime and y, and since we know that x prime is the square of our original design variable x, we've shown a parabolic dependence between x and y. And so that's it for the first task. The second task is about gradients. So we have to use gradient information to describe the effect of the design variables L and I on the displacement U of the given cantilever beam. And the necessary data is provided in a full factorial table that will be on the next slide. So we got this cantilever beam here, and we got some Young's modulus for the material, and we also got a force here at the end, and the force is given. And the objective function is the displacement u at the tip, and this displacement depends on the length of the beam and also on the inertia. So length and inertia are our design variables. For the first task of 3.2, we have to approximate the gradient at x1 and approximate the value of u at x2. And then we have to compare the approximate gradients with the exact values. Okay, for the first task, we assume that we don't know the closed form solution, so the analytic dependency between the displacement and our design variables. What we do know is those data points here in the grid, and those are all given here in this full factorial table. So we got two elements in this task. First we have to approximate the gradient. So to approximate the gradient, we'll use central finite differences. So for each of the design variables, we're going to look at this point, x1, and then we're going to look at the two neighboring points. So for du over dl, so the approximate gradient with respect to length, we're going to look at those 2 points where we keep the inertia fixed, and look at the two neighboring points for L, and for the other design variables, so the gradient with respect to I, with respect to the inertia, we'll keep L fixed here and look at those two neighboring points. We'll also find those values in the full factorial table. So we need those two rows where L is fixed and we have different inertias, and we're gonna need the fixed inertia and a different L. So that's those two. For the second element in this task, so the approximate value of u at x2, we see that x2 is not within this grid. So it's somewhere between the sample values that we know. Maybe it's somewhere here. Okay. So to find these, we start from x1. So that's what we know. And we also know the approximate gradient. So we go the delta between those two in approximately that direction. And then we get the value for u2. Now we got a plan. What we want to do, we just have to plug in some values. Okay, central finite differences in general for a function that depends on two variables can be computed according to this formula. So the partial derivative of f with respect to the design variable xi is f of xi plus delta xi minus f of xi minus delta xi, so that's the two neighboring points, and we divide it by 2 times delta xi. So we take the rows that we indicated on the previous slide, and we're gonna write them down here again. So for L, we got L of x minus 1 and L of x plus 1. We got U, so we got L is 966.67 for minus 1, and plus 1 is 1100 millimeters. I is fixed at the 14,063, so at the value for x1, and that's the same. And U is 0.196 and 1.5024. df over dl at our point x1 is then L at x1 plus 1, 1.5024 minus 1.0196 over 2 times and now we need delta L. .67, and we get a value of 3.62 times 10 to the minus 3, and that doesn't have a unit because F is in millimeters, that's the displacement, and L is also in millimeters, that's the length. For I, we have the same, so we got I of x minus 1 and x plus 1. We got U 4.1547.326. Then we got L which is fixed in this case, and we got the different inertias, 0.8 and 2396. Okay. dF over di at x1 is this minus this. So the displacements at the two different points over 2 times the delta and this is approximately this is equal to minus 1.74 times 10 to the minus 4, 1 per millimeter to the power of 3. So that's the gradient at x1. We're going to write it down here both together. So that's dF over dL and dF over di. And now we need to approximate the value at x2. So we're gonna interpolate. So u2, which is the value of u at x2, is u1. So the value of u at x1 plus, and now we need the delta, and we need to multiply that with the gradient. So we have to go from u1 in the direction of the gradient, and we know how far, and that's from the delta. So if we write that down in the using the vectors, we have delta L and delta I, and then we got the two partial derivatives, dF over dL and dF over di. Using the values, did it here, we know that u2 is u1, so 1.2454 plus delta L, so that's 1040 minus the 1033.3, and we need delta I, which is the 15,000 minus 14,063, and we the transpose of that, and then times the gradient, which is what we've already written down here. And we finally get 1.11 millimeters. Now we have to compare the gradients and the displacement with the exact values. So now we remember that we actually know the formula. So the formula for the displacement, which is f of L and I, which is f times L to the power of 3 over 3 times E times I. Okay, we compute the partial derivatives, df over dl, which is 3 times f times L squared over 3 times E times I. 3 is cancelling out, and we got df over di, which is minus f times L squared over 3e, and then we got I squared. Now we know that we want to compute the gradients at x1, so we plug in the values at x1. F and E are always the same, 10 newtons and the 210 gigapascal. And then we have L, which is 1033.3 millimeters squared, and I, which is 14,033 millimeters to the power of 4, and that's 3.62 times 10 to the minus 3. We do the same for the second partial derivative. And that's of course to the power of 3, because that doesn't change. Over two. Yep. And then we have minus 8.85 times 10 to the power of minus 5 and 1 per millimeter to the power of 3. Finally, we want to compute the displacement U2, and in this case we don't have to do any interpolation, we just use the formula. So we know F times L to the power of 3 over 3EI, and that's 10 times, now we have L at x2, which is 1040 millimeters over 3 times E times I, which is 15,000 millimeters to the power of 4, and then we get 1.19 millimeters. To compare them, well, if we remember, that's basically that one, so the first part of the gradient, first element, first partial derivative, that's basically the same value, so that's really good. For the second partial derivative, Before we had minus 1.7 times 10 to the power of minus 4. So that's well, not the same, but we got the same sign, and we also got kind of the same direction, so it's not completely off. For the displacement, 1.19 millimeters. Before we had 1.11. That's like a 6% error. It's not that bad. For the last task, how could the accuracy be increased further? So the accuracy is mainly how can we compute the gradient more exactly or approximate it, and the easiest thing to do is just use a smaller step size. So if we use a smaller step size, we get a more accurate gradient. You could also use like higher order approximations or stuff like that, but working with the step size is probably the easiest possibility. And that's it for the second task of this exercise. Okay, for the third task we have to calculate a one-dimensional regression model for the displacement with L as independent variable at a certain value for the inertia. So we got the same cantilever beam than in the last exercise, in the last task 3.2, and we got the same full factorial table here. And for the one-dimensional regression model we need values for different L, so for different length, at I is 4218. So those 4 rows, basically. Good. Okay, so the regression model is that we assume a function f hat that is x tilde times beta. So it's basically a linear combination of our design variables. And for the univariate case, so if we just got one design variable, it's just a simple linear equation. How do we compute the coefficients beta 0 and beta 1? We know that our objective function, so our original objective function, is the linear regression model plus some error epsilon. So we probably don't know this one, and we want to find a simpler function, f hat, so we choose it in the form of this regression model, and we have to want to find beta 0 and beta 1 such that the error epsilon is minimized. So we know that epsilon is f of x minus f hat of x, and we know what f hat of x looks like, which is this linear equation, and we know what f of x, we don't know what f of x looks like, but for the sample values we've given, so the sample data xa and ya, we plug that in here, so we know that that's ya, so the results, minus, and then we got beta 0 plus beta 1 times xa. And since we want to minimize the error, we take the absolute value because it's an error, and then we build the partial derivatives, set them to 0, and then we got those nice formulas here for beta 0 and beta 1. But it's important to remember that those only work if we are in the univariate case, so those only work if we just have one design variable. But luckily that's the case here, so we can use the formulas. First we have to, well, let's start from the beginning. That's what we want to compute. We want to compute our one-dimensional regression model. and it will look like this: beta 0 plus beta 1 times x. And first we compute the means. So x mean, we take those values from the full factorial table 2 slides ago. 900 plus 66 plus 33, 1100, and that's 1000. So basically in between, it's the middle of those 4 values. And then we got y mean of 2.7429 plus 3.3986 plus 4.1514 plus 5.0079, and that's 3.8252. And so that's the mean of the values for U. And that's the mean of the values for L. Now we can compute beta 1 as 1 over n. We use those formulas from task 3.1. Sum over A, X, A, N, Y. The means over the variance of the design variable. If we plug in the values, we end up at it's a lot of 2's. 0.0113, and that leaves us for beta 0 with 8252 minus 113 times 1000. And that's minus 7.4966, and this one has the unit millimeters. So we got the coefficients now, but the task was to calculate the regression model. So it's actually an important last step to write down the regression model. F of x, or in this case we can write f of L, is minus 7.4966 millimeters plus 3 times L. In the case when you don't have just one design variable, but more than one, so D in general, you can't use the nice shortcut anymore, and you have to use the general formula for beta, which is derived in the same way as before. So you want to minimize the error, and then you want to find the coefficients that minimize the error, and you end up with that formula. We'll apply this formula to the same task. First we have to build the matrices X and Y. So remember that X has 1s on the first column, and then the values for L in this case, which is the first design variable. And Y in this case is just a a vector of the values of u, also of the different displacements. So beta is xt times x, and inverting it and then multiplying it by xt again, and finally by y. So if we do that, I mean, you know how matrix multiplication works, we'll end up with minus 7.4966 and 0.0133. Again, we wanted to compute the regression model, so let's write it differently. In this case, we have f hat is x tilde times beta, so x tilde times minus 7.4966, and of course that's millimeters, and 0.0133. X tilde, just to remember, is 1 and x1 in this case. Okay, so luckily we arrived at the same numbers for the coefficients as before. Well, of course it has nothing to do with luck. And we've written down the one-dimensional regression model. So for the displacement with respect to the length of the beam. And that's it for the regression model task. Okay, so the computer exercise in this third exercise deals again with the cantilever beam we already know. For the first task we have to implement a full factorial design. Then we have to compute the correlation coefficients, again for this value of a certain value of the inertia, as we did in the previous task, and also including all the inertias between a lower bound and an upper bound. Then we have to create a Monte Carlo table, so that's what we haven't seen so far, that's the random sampling, and then compute a linear regression model based on the Monte Carlo table. And finally we have to answer a little question, so what's the difference between a gradient and a regression coefficient? We provided a before MATLAB script on Moodle, and you can go through there and do all the tasks. They are not in a sequential order. So you'll find commented sections like you did in the last time, in the last exercise, but you won't have it quite as nicely sequentially, but I'm sure you'll manage.
So this is the MATLAB script for the cantilever beam. As the first exercise, we have to implement a full factorial design. So full factorial, that's already set. And first we have to set the number of levels that's given in the task 4, and then compute the number of samples. So that's given, formula is given in the exercise and also in the lecture. That's number of levels to the power of number of parameters. So n parameters is given up here, that's 2, L and I, and so we compute the number of samples. Now it says here we have to go to line 116 to distribute the sample points according to R. So we go to line 116, and for now we got R, which is a matrix with 2 columns where all the different combinations of the 2 variables are given, but they are only between 0 and 1. So now we have to kind of move them to be between the boundaries of the design space that we actually do have. So we go from a lower bound plus R. So we take the first column because that's for our first design variable L. We take the first column of R because that's for our first design variable L. And we multiply it with L lower bound, upper bound, minus L lower bound, so that's basically the delta. And we do the same for I. And the rest is already implemented, so our full DOE so our full factorial table, we can have a look at it, is we got here our values in the first column, our values for U, so the system response, we got the values for length here, and we got the different values for I here. So if you're interested, it's basically exactly the same table that's also given on the slides. Okay. That's it for the first task. In the second task, we have to compute the correlation coefficient. So for A, we only need a fraction of the full factorial table. And so first we have to take out those relevant rows that correspond to I at 4218, so for this certain inertia. And if we look at our DOE table, that's the first and the 5th and the 9th and the 13th row. But we want to make it a bit more sophisticated, so we say we go from 1, because that's our first, and we got 1 for each level, and that's for all the samples, so from 1 to the end basically. And then our relevant data, we take out only those rows. Okay, now we just have to type in the formulas for mean, standard deviation and covariance. In this case, we can do it for the whole table. And along the first dimension, so that's for each column. We can do the same for the standard deviations, so we take the square roots here. Times. And we take the square of each entry. And also along the first dimension. And we subtract the squared of the means. And for the covariance, we have to take the sum of y times x, so pointwise multiplying those two columns, and that's the sum, and then we have to subtract mean of y times the mean of x. So L in this case, because we want to compute the Pearson correlation coefficient between U and L. And now let's run it. And we got a Pearson correlation coefficient of 0.9982. In B, we have to use the whole DOE table. So instead of restricting ourselves here to just some rows, we just use the whole DOE table. Why don't we have to change the formulas here? Because even though we use different points for the inertia, we still want to compute the Pearson correlation coefficient between U and L, so that didn't change. Okay, now we got a Pearson correlation coefficient of 0.23, and before it was 0.98, so at for this certain inertia of 4,000 something, there's a pretty strong linear relation between L and U, but looking all over the whole design space, it's not as strong. Well, for different eyes, it's more like a plane. It's not. It's no longer just one linear equation, and we'll see that later when we plot it. Okay, for the third exercise, we have to compute a Monte Carlo table. So first we change our sampling method from full factorial to Monte Carlo. And then we'll look for our Monte Carlo here. So how many samples do we want? We want 30 experiments, so 30 samples, and we compute our matrix R with the rand function. So rand has several input parameters. In this case we use the 2 dimensions, so along the first dimension we need 30, and along the second number of parameters. Look at the E again. And that's it. Now if we look at our value R, we got 30 different combinations of those two values, and now we also have to shift them so they are between our upper and lower bounds, but that's what we already did for the full factorial sample. So if we continue, we already got that, and then we have our DOE table. Here, which is our values for U, so for the displacement, for different random values of L and also of I. Now we have to compute a overall linear regression model, It's the last task. So first we have to define our matrices X and Y. So X in the first column always has ones. So it's ones and in the second it's got x1, so our first design variable, which is L, and that was in the second column of our DOE table. And then we need I, which is in the third column of our DOE table. Y is the vector of the system responses, which in this case is in the first column of our DOE table. Okay, to compute the regression coefficients, we just use the formula. We have to take the transpose of x times x and then compute the inverse and then multiply it by the transpose of x again and finally by y. And then finally we have to calculate the regression model. So in this case it's a function which is beta 0, so the first coefficient plus beta 1, it's the second coefficient, and beta 2 times I, so that's the third coefficient, and then we can plot it, and that's already implemented. So looking at it, we got here our objective function as it would look well analytically, and then we got the random values that are distributed randomly over our design space, and we got a linear regression model that that's somehow approximating this objective function. Well, if you do it, it will most certainly look different from mine. That's because, well, we use random points, and depending on which points you use, this might slightly look different. But it still should look, well, similar. That's it for the computer exercise. We got one little task left in the PowerPoint on the slides, so we'll go back there now.
Okay, at last we have to answer a little question. What is the difference between a gradient and a regression coefficient? So we know by now that we can't write with a laser pointer. We know by now that a gradient provides us with local information, and the regression coefficients provide us with global information. So if we just use a very simple plot of the cantilever beam again, it will look like something like this. So displacement over length. If we want to compute a gradient, let's do the gradient in green. We can compute the gradient at this point, and it's some kind of line. Or we can compute a gradient at that point. So it's also always a snapshot of a sensitivity at one particular point in the design space. Maybe you can say before in the task when we approximated the gradient we used different values, so we didn't just use 1 point, but that was simply for the approximation of the gradient. We still try to compute the gradient at one specific point. If we want to compute the linear regression model, we'll choose some boundaries, so maybe from here to here, or we choose various points on that line, and we compute a linear regression model for all those points. So it's used to build a linear model that approximates the function over a certain part of the design space. That's it for the third exercise. I hope you, well, enjoy is maybe the wrong word, but you understood it, and enjoy a long weekend, and then I'll see you next week.